Welcome students to lecture number 2 on conductance. In the last lecture we have studied about conductance, specific conductance, and we have also studied about the units for conductance and units for specific conductance. In this topic we are going to study about equivalent conductance. What is equivalent conductance? It is defined as the conductance of a solution containing 1 gram equivalent of an electrolyte placed between two sufficiently large electrodes which are 1 centimeter apart. So, what is this 1 gram equivalent? 1 gram equivalent of an electrolyte means the equivalent weight of that particular electrolyte. So that solution will contain 1 gram equivalence, that is the equivalent weight of that particular electrolyte. And this solution is placed between two sufficiently large electrodes which are 1 centimeter apart. Or it can also be defined as the conductance of that volume of the solution containing one equivalent of an electrolyte, and it is denoted by the symbol lambda. Let us consider V centimeter cube of the solution containing one equivalent of the electrolyte. So this much volume in centimeter cube contains one equivalent of the electrolyte. And when you measure the conductance, that conductance of the solution is called as equivalent conductance, denoted by lambda. Also, last time we have studied the conductance shown by 1 centimeter cube. If you remember, 1 centimeter cube solution containing this electrolyte is called specific conductance. Here we are not talking about, when we talk about specific conductance, we do not say that it contains 1 gram equivalence. 1 gram equivalence is only in the case of equivalent conductance. In specific conductance, we are talking about the solution which is placed in a cube which has all sides equal to 1 centimeter. You remember last time we had discussed about a cube. Each side is equal to, if this is connected to the positive and the opposite is connected to the negative, the solution which it contains, the conductance corresponding to that solution will be called as specific conductance. Now the conductance, if we sum this up, what we have said in the first point, the conductance of V centimeter cube is equivalent conductance, and the conductance of 1 centimeter cube is specific conductance given by K. Then I can put these two things together and I can write equivalent conductance is equal to specific conductance into volume of the solution. We number this equation as equation 3. Now, writing the same thing in words, I have equivalent conductance is equal to specific conductance into volume of the solution in centimeter cube containing 1 gram equivalence of the electrolyte. Okay. Now this volume I can write as volume in cc. I can write it as 1000 upon n, where n is the normality of the solution. So if I substitute this volume in equation number 3, then you will get equivalent conductance is equal to specific conductance. In place of volume, we are going to write this 1000 upon N. This is written in place of volume. Now, what will be the units? What will be the units of this equivalent conductance? If you remember the units of specific conductance, units of equivalent conductance, I'll just write the formula for you. Equivalent conductance is equal to specific conductance into, we have 1000 upon N. So here K, the units of K specific conductance is per ohm per centimeter, and the units for this normality will be equivalence per centimeter cube. Equivalence per centimeter cube, or you can say equivalence centimeter minus 3. Okay, the volume is in centimeter cube. So, if you cancel out 1 centimeter inverse from here and 1 centimeter inverse from here, what will remain in the denominator is centimeter minus 2. This will get cancelled out. This will get cancelled out with 1 centimeter minus 1 from here, and what remains here will be centimeter minus 2. This centimeter minus 2, when it goes in the numerator, we can write it as centimeter square ohm inverse, and equivalence, when it goes in the numerator, it will be equivalent minus 1, equivalent inverse. Okay, or you can also write the units as centimeter square instead of per ohm. Per ohm is the unit of conductance. We can write mhos is also the unit of conductance, and equivalent inverse. Or the other way of writing is, instead of centimeter square in the SI unit, you can write it as meter square. Instead of mhos, the SI unit is Siemens, equivalent inverse. So these are the units of equivalent conductance. Next, we move on to what is molar conductance. It is the conductance of that solution, of that volume of the solution containing 1 mole. In equivalent conductance, it was containing 1 gram equivalence. Here it contains 1 mole of an electrolyte, is known as molar conductivity. You all should know what is meant by 1 mole. 1 mole is that quantity which contains Avogadro's number of particles. It is denoted by lambda m or mu. It is related to specific conductance K by this particular formula. We have mu is equal to K into V, that is molar conductance is equal to specific conductance into volume. The formula is the same, or almost the same, only when we substitute volume. Here the concentration is in terms of molarity, whereas in equivalent conductance it is in terms of gram equivalence. So it is mu is equal to K to 1000 upon N. Volume is 1000 upon N. The units of molar conductance, you can work it out the same way as we have done for equivalent conductance. It is centimeter, it works out to centimeter square ohm inverse mole inverse. Instead of ohm inverse, we can write it as mhos also. So this is another way of writing it, how we have written there. So I write here or, so instead of ohm inverse, we can write it as mhos, or we can write it as meter square cement mole inverse. Now, the next is effect of dilution on conductance. What is the effect of dilution? If I dilute the solution, what will happen to conductance? What will happen to specific conductance? What will happen to equivalent conductance and molar conductance? Now, conductance of a solution is due to the presence of ions. We have said conductance of the solution in the last lecture, you know it is because of the ions. More the number of ions, more is the conductance. I want you to remember this. More the ions, more is the, more the ions, more is the conductance. Okay. So less the ions, less will be the conductance. Now let us see this. What is the effect of dilution? What do we mean by that? Effect of dilution. It means you are diluting the solution. You are adding the solvent. Okay, suppose you have 10 ml of the solution. You are making it 100 ml by adding water. So that is called as dilution. Now, what will happen to the conductance? Will it increase, decrease, and why it will increase and decrease? Now, conductance of a solution is due to the presence of ions, and since on dilution, dissociation increases. Okay, this what I have underlined, you have to remember. More the number, first thing what you have to remember here is this. More the number of ions, more is the conductance. Second thing you have to remember is when you dilute the solution, these are points to remember. What I am marking 1 and 2 are points to remember. On dilution, the dissociation increases. What does that mean? What is meant by dissociation? More amount of the electrolyte will dissociate to give you the ions. So when you dilute the solution, if the dissociation increases, what happens to the number of ions? The number of ions will increase. So number of ions increase. So when the number of ions increases, I have mentioned to you in point number 1, more the number of ions, more will be the conductance. Okay. So conductance will increase when you dilute the solution. Let's see what happens to specific conductance. Specific conductance depends upon the number of ions present per centimeter cube. You remember we have considered this in a cube. The solution which is present in 1 centimeter cube of an electrolyte. See, if this side is 1 centimeter, all the sides of the cube are 1 centimeter, and as I have told you, if this is connected to one electrode, this is connected to one electrode, and if you fill this cube with a solution, that conductance will be the specific conductance. Now, we have said specific conductance depends upon the number of ions which are present per centimeter cube or per ml of the solution. So if you are going to dilute this solution, what will happen per centimeter cube? If you are going to dilute the solution which is present here, you take it out and you dilute the solution and then you fill this box again. So the number of ions in that will decrease. So on dilution, the number of ions per centimeter cube will decrease. Are you following me? So if the number of ions per centimeter cube decreases, then specific conductance is said to decrease with dilution. So you have to be very clear with these concepts. Now, what is the effect of dilution on equivalent conductance? Can you think for a minute and tell me? First of all, you have to know what is equivalent conductance. It is that volume of the solution. Think and tell me. It is that volume of the solution which contains 1 gram equivalence of a electrolyte. So, equivalent conductance increases on dilution. Why? Why do you think equivalent conductance increases on dilution? I have used short forms here. Please make a note. Equivalent conductance increases on dilution due to the fact that equivalent conductance is the product of specific conductance and volume. So we have equivalent conductance. This was our formula. Specific conductance into volume. So just now we have seen with dilution, specific conductance decreases. But what happens to the volume of the solution when you dilute? When you dilute, the volume of the solution increases. Volume of the solution increase containing 1 gram equivalence of the electrolyte. Now, decreasing value, please make note of the short forms I have used here. Decreasing value of specific conductance is more than compensated by the increase in volume. What does that mean? Increase in volume is more than this decrease. Okay, decrease in the value, specific conductance is decreasing, but volume is increasing. So the volume is much more than the decrease. So decreasing value of specific conductance is more than compensated by the increase in volume. This value will be more. It increases. The increase is more than the decrease when you put the numerical values. So that is why the equivalent conductance will increase on dilution. What is the effect of dilution on molar conductance? Again, like the same way what we have discussed, molar conductivity increases with dilution as the total volume. Here also we use the formula molar conductivity is equal to specific conductance into the volume. So volume of the solution containing 1 mole of the electrolyte increases. The volume increases on dilution. So upon dilution, the concentration is decreasing. When the concentration approaches 0, the molar conductivity of the solution is known as limiting molar conductivity. This we will be discussing little later. That is, when you dilute the solution. So let us make the things very clear. Molar conductivity increases with dilution, the same way how equivalent conductance increases with dilution. Now this is the second thing that you have to remember here. Upon dilution, when you are diluting the solution, the concentration of course decreases. When the concentration goes on decreasing, it approaches say 0. The concentration is very less. Okay, you are diluting it to a very large extent. The molar conductivity of the solution at that time, the molar conductance will be called as limiting molar conductance. That is when the concentration is 0, when the solution is very dilute. The molar conductance will be called as limiting molar conductance, or it will be called as limiting conductance sorry, it will be called as molar conductance at infinite dilution. So limiting molar conductance or limiting molar conductivity is also called as molar conductivity at infinite dilution. I have shared a link here. You can click on it and check a YouTube video which gives you the information about the effect of dilution. Now, if you look at this, uh, here what we have plotted is molar conductance. Okay? Molar conductance against concentration. So, if we move in this direction, the concentration goes on increasing, square root of concentration. So concentration goes on increasing. If we move in this direction backwards, concentration goes on decreasing. When does concentration go on decreasing? Concentration goes on decreasing with dilution. Okay, so as we move in the opposite direction, concentration decreases, or you can say dilution. You are diluting the solution. Dilution increases. Okay, if we move in the opposite direction. So dilution is increasing. Now, if I plot a graph like this for strong electrolytes like KCl and HCl, these are strong electrolytes, you get a straight line graph. You will get a straight line graph like this. And if you extrapolate this line, if you extrapolate, you can see the dotted lines there on top. If you extrapolate that line, then at this point, the concentration is 0, isn't it? At this point, concentration is 0. It means the solution is very, very dilute. Very, very dilute solution. So this point where concentration is 0, where when we extrapolate the curve and it meets the y-axis, this term is called as, or this point is called as limiting molar conductance. It is written as lambda m infinity. Okay, so you can see it is written here. It is lambda m, and this is nothing but infinity. Okay, written like this, or sometimes it is written as lambda m naught. So same thing, lambda m naught or lambda m infinity. Now this is for strong electrolyte. So you can see for KCl, this is your lambda m, and this is your lambda m for HCl. That is, it is limiting molar conductivity. It is limiting molar conductivity, or it is molar conductance at infinite dilution, when the solution is very, very dilute. So because you are getting a straight line graph like this for strong electrolyte, it is possible to find out equivalent conductance or molar conductance at infinite dilution of strong electrolytes. But in the case of weak electrolytes, when you plot molar conductance against square root of concentration, you don't get a straight line as you get in the strong electrolytes, but you get a curve like this, somewhat an exponential curve like this. So how do we find out lambda? How do we calculate lambda and molar conductance at infinite dilution? Because if you extrapolate this curve, it does not meet the y-axis. It is almost parallel, you can see it goes almost parallel to the y-axis. So it becomes difficult to find out lambda infinity, lambda and infinity, that is limiting molar conductance or molar conductance at infinite dilution for weak electrolytes. For strong electrolytes, you can extrapolate the line because you get straight line curves there, and you can find out lambda and infinity. For weak electrolytes, we cannot find out using the curves. So, for weak electrolytes, we make use of Kulrauch's law. K-O-H-L, Kulrauch's law of limiting molar conductivities. Okay, so to find out lambda infinity for weak electrolytes, we make use of Kulrauch's law, which we will be studying in the next lecture. So you can see here, I have taken this graph from the net. You can see this is for strong electrolytes. You get a straight line graph, and when you extrapolate this, it meets the y-axis to give you lambda infinity. So you get lambda infinity values here for the strong electrolyte. So this is lambda infinity for KCl. Whereas for acetic acid, it becomes difficult. We cannot extrapolate and find out lambda infinity when the concentration is 0, because it goes almost parallel to the y-axis. In case of strong electrolytes, when the concentration approaches 0, the molar conductivity attains a value known as limiting molar conductivity. It is given by lambda naught n. But for weak electrolytes, you cannot find out this using the graph, but we will use Kulrauch's law to find out lambda infinity for weak electrolytes. Okay, next is the factors affecting the conductance of the electrolyte. On what factors does the conductance of the electrolyte solution depends? First is the temperature. The conductance of an electrolyte solution increases with the increase in temperature due to the increase in the extent of ionization. What do we mean by ionization? Ionization is nothing but formation of the ions. So, when the temperature increases, as temperature increases, ionization increases. Ionization increases means there are more number of ions, that is ions increase, and as a result conductance will increase, because conductance depends upon the number of ions. So when the temperature increases, it will facilitate the dissociation. Dissociation is the same as ionization. It will form more ions. Next factor is the ionic size and mobility. Ionic size and mobility. The ionic mobility decreases. Mobility means the movement of the ions. The movement of the ions decreases with the increase in its size. If the ion is larger in size, it will not be able to move faster. Hence, the conductivity decreases. Okay, so it means if the size is big, what happens? It cannot move faster. Ions cannot move faster. So if they cannot move faster, conductance decreases. It decreases the conductance of the solution. Mobility is a very important factor in conductance. If the ions can move fast, then the conductance increases. They carry a more amount of the current when they are moving. Next factor is the nature of the electrolyte. Nature of the electrolyte. The strong electrolyte undergoes complete ionization. We have weak electrolytes and strong electrolytes. We have seen that in our first lecture. There is complete ionization in strong electrolytes, and the weak electrolytes there is partial ionization. So if it is a strong electrolyte, there is complete ionization, and hence they will show higher conductance, and because there will be more number of ions, whereas weak electrolytes undergo partial ionization and hence show comparatively low conductivities in their solutions. Next factor is the nature of the solvent and its viscosity. So what is viscosity? You have seen honey. If you pour it, it will not move very fast, whereas if you pour water, water moves very fast on any inclined surface. If you pour water, it moves faster than honey. So we have to say honey is more viscous. So that is viscosity we are talking about. So if we use a solvent like honey, that type of a viscosity, or that having higher viscosity, the ions in that particular solution will not be able to move fast. So when the ions cannot move fast, the conductance decreases. So ionic mobility is reduced in more viscous solvents. If the solvent is less viscous, conductivity increases. If it is more viscous, conductivity decreases. The next factor is the concentration. The conductance of a solution is due to the presence of ions in the solution. We all know that. And since on dilution, the degree of dissociation of the electrolyte increases. You remember I had put it as number 2 somewhere in one slide. When you dilute the solution, there is more ionization, there is more dissociation taking place. So there will be more number of ions. And as a result, it is expected that the conductance of the solution increase on dilution. We have explained this point somewhere earlier also. So if the concentration decreases, that is, you are diluting the solution, on diluting, the ionization increases, and as a result, the number of ions increase and conductance of the solution increases. For your reference, you can refer to the link given here on the YouTube channel. Also, you can refer to Advanced Physical Chemistry book, the link for the online ebook. Okay, you can click on this and check it out. Thank you, girls.